All right, so let's go ahead and talk about sort of our goals in picking a model. So we've talked about now R squared and adjusted R squared. We've talked about the idea that we want to maximize the amount of variation explained given the data that we have. But sometimes the best model is not the most complicated model, right? We could add a ton of stuff in, maybe even that stuff is reasonable, but sometimes we want a simple and elegant model that can explain a lot of variation without being too complicated. Sometimes that means that including variables that are not important can actually reduce the accuracy of the predictions, and that's not something that we want either. So we're going to talk now about model selection strategies, and model selection strategies allow us to eliminate variables in a systematic way, and those variables will be less important, right? So we're going to get rid of the less important ones in a systematic way. That's a model selection technique. And it's common to refer to these simple models with the unnecessary stuff gone as parsimonious, right? So parsimonious is sort of like a money-related term. It can mean like stingy or cheap, but basically what you're looking for is a model that's going to give you the best bang for your buck. Okay, so if we go back to our data set, we can look at all of the variables. We've got high temperature, we've got low temperature, we've got average temperature, spring, summer, fall, cloud cover, precipitation, volume, that's our response, weekday, day type, which is just another name for weekday. They've coded it differently, I don't know. And then we have season, but we're not going to use that one. That one was from an example before. So the model with all of the available explanatory variables is often referred to as the full model, right? If you're using everything that you have, basically the model that you end up fitting is called the full model. Okay? For the rail trail data set, we're going to exclude these last two because they're repeated elsewhere in the data. The full model predicts volume from the day's high temperature, low temperature, average temperature, season, spring, summer, or fall, cloud cover, precipitation, and whether the day was a weekday. We used to have the day was wet, but we're getting rid of that as well. I'll fix that on the slides. Okay, so here we have our full model with all of those coefficients in the variable. And you can see here I've got a lot of output, lots of decimals, so I'm going to go ahead and round it so that we can see better. Here is the summary of our full model. Okay, and you can see, first of all, we're going to look and see that the R squared is a pretty high, right? It used to be 35-ish and now it's 47-ish. But we can also see, if we look at the column of p-values on the end here, that not all of our variables are significant, okay? So maybe we want to go ahead and try to get rid of one of these variables, okay? And we're going to see if dropping any of those variables, removing them from our model, increases the R squared. Okay, now, which one are you going to drop first? Okay, we're going to think about this. We have p-values, right? We've got that information. We know that low p-values mean that there is a significant relationship, and higher p-values mean that there are not significant relationships. So I'm going to start by getting rid of the variable with the highest p-value. Okay, now let's see, let's go back. Over here in the last column, that is the summer variable. So I'm going to go ahead and get rid of that summer variable. You can see it's not here. And my R squared has actually bumped up a little bit. So I got rid of a variable and I have my adjusted R squared going up a little bit. So this one is actually better now that I've gotten rid of that extra variable. Okay, now if I remember correctly, what I did next was look at this low temperature, which has the next highest p-value. I'm going to actually drop low temperature from the full model and see what happens, because I don't want to get rid of summer if I'm not also going to get rid of spring. So I'm going to kind of go back, stick summer back into my model and get rid of low temperature. And you can see that our r squared is about the same. So we're going to leave that out. It's about the same, so it's not really helping. It's not leading to a big fat increase, so we're going to keep that out. Summer's got the next highest p-value now that it's back in, so let's try getting rid of it again. Oh, I didn't get rid of that one. I left it in. Sorry, we're going to try to get rid of average temp since that's also got a pretty high p-value. And now we're getting somewhere, right? We've got another adjusted r squared of 0.473. So we're making progress. The p-value on summer has gotten super high, so now we're actually going to get rid of it for good, I think. And I went ahead and dropped spring as well, since those are kind of combined information. You can see that my r squared has gone up a little bit again. And I'm looking at some pretty significant variables, right? I've got high temperature left, that's got a very low p-value. Cloud cover also looks pretty significant, as does precipitation. And weekday is kind of borderline, so let's go ahead and get rid of weekday. It's got the highest one. And you're left with this model, my model 7. I've fit quite a few. It's got an adjusted r squared of 0.466, which is almost as good as the maximum r squared that we have, but we also have the added benefit of only having 3 variables. And this is a really simple and sort of elegant way to say that the volume of people on the rail trail depends on the day's high temperature, it depends on how cloudy the day is, and it depends on if there was rain. Okay, and we can see high temperature has a positive slope, so the higher the temperature, the more people will be outside. Cloud cover's got a negative slope, as does precipitation. So if you've got more precipitation, you're going to have a number of riders go down. If you've got more clouds, the number of riders is going to go down. If you've got higher temperatures, the number of riders is going to go up. This is a pretty nice looking model that really backs up our intuition. Okay, the model selection strategy that we have just used is called backward elimination. Okay, so in backward elimination, we start with the full model, we start with everything, we identify the predictor with the largest p-value, and we drop it. Okay, especially if that p-value is not significant, right? So we don't do anything if they're all significant. We wouldn't drop any. If that p-value, if that big p-value is bigger than 0.05, we drop it, we refit the model, and we try again, right? And we keep doing this until we have a model with all significant predictors. Okay, that's called backward elimination, and we used p-values to eliminate the variables there. So it's backward elimination with the p-value approach.